Now, Dr. Ravi Kumar, Professor of Ceramics in the Department of Metallurgical and Materials Engineering at IIT Madras, will talk with us about ceramics. Please, Dr. Ravi, you can start now.
Can you see the presentation?
Yeah. Please.
Yeah. Thank you. Good afternoon, everybody. And thank you for the organizers for inviting me to present this talk. I know that it's a metallurgy department. I am also from metallurgy department. However, my talk will be mostly on ceramic materials because I work on ceramics. My laboratory is called High Performance Ceramics. And recently, we have incubated a company based on the work that we have done. So I'm also the chief consultant and co-founder of the company Saratattva Innotech Private Limited. So as I've been introduced, I'm from IIT Madras. IIT Madras is a federally funded institute by the government of India. And this is my group. So I acknowledge, so mostly we work with the Indian Space Research Organization because for all the rocket programs, we require materials which should withstand more than 1400, 1500 degrees Celsius. So we work on developing ceramics for the Indian Space Research Organization. So we are funded by them. So we gratefully thank the Department of Space, Government of India for this. My lab specifically focuses on three aspects of design of ceramics. We work on producing ceramic materials which are meant for space, so for security, defense, and so on. So we have been working on structural ceramics for quite some time. And apart from that, we also work on ceramics for energy and environment. We also work on producing hydrogen and so on. The previous speaker talked about hydrogen production. But for lack of time, I will restrict my talk only to materials which are used for structural applications. Otherwise, we work on materials for energy and environment as well. The interesting part is that we work on materials, we produce materials in-house here, and we design materials in-house from atomistic scale and design it up to microstructural and macro scale for fine-tuning the properties of materials. So we use polymer precursor route to making ceramic materials. It's not very much metallurgy. It's a lot of materials chemistry, but it's very important to have good control on materials chemistry because this producing ceramic materials through polymeric precursor route involves a lot of chemistry. So you can see that we actually individually synthesize these polymeric precursors and design what kind of ceramics that we want at the atomistic scale in the lab. And the idea of using them is unlike usual ceramic processing where you have to deal with powders, here the idea of using polymeric precursors and transforming them to ceramics gives us flexibility to cast them and to make composites and so on. So if you want to make ceramic matrix composites, the only way to make large-scale ceramic matrix composites for space or defense applications is only through precursor route. So usually when we are dealing with pre-ceramic polymers, we are dealing with temperatures in the order of around, say, from room temperature to 400, 450 degrees Celsius until we cross-link them. And then if you want to shape them, you have to shape them in this temperature range. And then we convert the polymer, depending on the chemistry of the polymer, the temperature can vary anything between 600 to 1200 degrees Celsius. And we convert them into ceramic materials. I hope you are able to see the slides, right?
Yeah.
So then we can produce them into very stable crystalline ceramics at 1400 to 1600 degrees Celsius. So we widely, it is a very interdisciplinary, highly interdisciplinary research. The most important thing is it's a powder-free process. Unlike a usual sintering, methodologies used by ceramic scientists, it's a completely powder-free process. As I said, it has to do a lot of materials chemistry. At the same time, it's very highly interdisciplinary. To work on this, one should have good control on chemistry. You should know ceramic science. You should know thermodynamics, and you should also be an engineer because you need to develop products. And therefore, this is a very highly interdisciplinary research. Not so easy to do it in metallurgy department because in metallurgy department, not everybody is good in chemistry, but I generally in my lab, I hire both chemists, engineers, and material scientists to achieve this. Just to give you an idea, so on the left-hand side, you are seeing a flow chart of how we make them at atomistic scale. We make this polymeric precursors and design them at atomistic scale. And then once you produce them, then we convert them into ceramics, and we can easily fine tune to the engineering application that we want. For example, here you can see a microstructural engineering where you can find very nice pores which are meant for, say, photocatalytic applications. And at the same time, you can see the high-resolution transmission electron micrographs here, where we show how to control them and how to make them extremely high temperature resistant, say from 1500 degrees Celsius to 2000 degrees Celsius by just microstructural engineering. For example, SiC means silicon carbide, Si3 and 4 is silicon nitride. They are already very high temperature resistant beyond 1200 degrees Celsius, but our objective was to work on them to make them stable till 2000 degrees Celsius. And this is the work that we were doing in the Max Planck Institute in Stuttgart a few years back when I used to do my PhD there, and we continue to work on this topic because it's extremely important for us, for the country. And there are two important challenges in this area, which actually limits our capability in defense and space. One is to make ceramic fibers. Not many people can make ceramic fibers. And however, this methodology is known very well. It was published in 1975 by the Japanese scientist Yajima. People know how to make them, and scientific papers are there. But there are a lot of technological challenges, and therefore not many people can make such ceramic fibers. For example, to make silicon carbide fiber, you need to produce polycarbosilane precursor, and you should know how to spin it and convert them into silicon carbide fiber. If you are not from the field, you may want to know that the silicon carbide fiber is important as reinforcement in silicon carbide matrices if you want to produce CMCs based on SiC and SiC, which many countries are not able to make them as of now because silicon carbide fiber is not available and not many people can make them. However, as I said, the papers are there, but not many people know how to make it. Just to give you an idea, for example, if you want to purchase polycarbosilane from United States of America, there's a company called Starfire Systems, and they charge like $3,120 per kg to purchase them. There are only a few companies which can make them. For example, Nippon Carbon in Japan, Ube Industries in Japan, Dow Corning in USA, and again CY in USA, and BGS Ceramics in Germany. Only 5 companies can make these kind of fibers and so on, because they're all patented and technologically very challenging. And if you want to really look at the costs that are involved to produce to purchase 1 kg of silicon carbide fiber, for example, depending on the quality of silicon carbide fibers per kg, it can vary from $2,000 to $12,000. If you really want to buy silicon carbide fibers, which can be used for strategic applications in space and defense, it's extremely expensive, like $12,000 per kg. But the problem is, even if you have money, I don't think you can get it because most of them are under embargo. You cannot really get them even if you want to buy them. And for example, India cannot purchase them either from Japan or America. So obviously it means that we have to produce them and we have to make them. And we in our lab, we have been attempting to make them, and we are now already partially successful in making such fibers, not only silicon based, but we are also now attempting to make non-silicon based fibers, silicon carbide and non-silicon based fibers based on transition metals. And again, they're all meant for strategic applications. So the left-hand side is basically meant for strategic applications in space, so that we can make ceramic matrix composites by incorporating or reinforcing these fibers. And then we have also produced our own centrifugal fiber spinning machine to make short fibers meant for functional applications, so that we are totally independent. Just to give you the chemistry part, I think I don't know how many of you understand the materials chemistry part, but we have been working on silicon-based precursors, and depending on what goes into the backbone here, you can actually make different kinds of materials. For example, if silicon and carbon is in the backbone, you are actually making silicon carbide to begin with. And if silicon nitrogen are in the backbone, then you make silicon nitride. If oxygen is in the backbone, then you make silicon oxycarbide. So it gives you a lot of flexibility. If you're a very good materials chemist, it gives you a lot of flexibility in making different materials. For example, we have worked on boron-modified silicon carbonitrides, and these boron-modified silicon carbonitrides are very stable till 2000 degrees Celsius, very ideal for extremely high temperature applications. We have done thermodynamic calculations. We have shown that they are extremely stable till 2000 degrees Celsius. Again, this was work done in collaboration with Germany. When I was in Germany, we produced them. And again, we have been continued to work with them, and these materials are very useful for strategic applications. And there are challenges in making these precursors, and again, at the same time, one has to take care how to engineer the microstructures to make them extremely stable at 2000 degrees Celsius. Indian space program, I think it was initiated sometime in the mid-70s, 1970s, and for our elaborate space program, where we build both the space launch vehicles as well as spacecrafts. For us, I think the ceramic matrix programs are very much useful for the rocket industry, and this is a reusable launch vehicle that Indian Space Research Organization is producing and already has tested it. And for fully reusable rockets, and we need, for example, apart from making ceramic matrix composites, we also require, using ultra high temperature ceramic coatings, which can withstand 2000 degrees Celsius, particularly for hypersonic applications and so on. You need to coat very high temperature resistant materials. Again, for coatings, again, it's a big challenge. So we have been working on non-silicon based materials. As you see here, we have been working on rare earth based ceramics. And the whole challenge here is to make these ceramic coatings, we don't use ceramics directly. What we do is that we make polymeric precursors where in the backbone of the polymer, we have all the elements that are required to produce the high temperature ceramics like zirconium boride or zirconium carbide. In this specific case, I'm showing you borides and carbides of zirconium, but we can also extend it to hafnium carbide, hafnium boride, tantalum carbide, tantalum boride, and so on, which all of them have high temperature stability beyond 2500 degrees Celsius. So this again we have been working on, and for quite some time, for about nearly 2 years, and we have done some basic studies. And as you can see from the X-ray diffractograms, when we make them, the first thing that we do is that we test their high temperature capability, and you can see that at 1600 degrees Celsius, the ceramics is completely amorphous, and which is good for us because we want them to be amorphous, and because amorphous materials are more stable, although it is thermodynamically not very stable, but we make these thermodynamically metastable as stable as possible so that they can be used for extended duration of time. For example, here it is shown to exhibit, nanocrystals, but extremely small, fine nanocrystals of, say, lanthanum-based zirconate or zirconium carbide when they were exposed to 1600 degrees Celsius for about 16 hours. So this is what we want. We want materials which can be very stable. Of course, we could have tested beyond 1600. We had some difficulties to go beyond 1600 degrees Celsius because operating furnaces beyond 1800 is also a challenge, and therefore we are restricting the studies to 1600 as of now. And if you look at the high resolution transmission electron micrographs, just to give you an idea, you can see very fine nanocrystals of the phase that we want. So we can engineer what kind of crystals that we want. For example, the high resolution transmission electron micrographs indicate the presence of lanthanum zirconate and zirconium diborate. Both are very important for us. Zirconium diboride is very important to produce or to retain the high temperature stability. Lanthanum zirconate helps us to increase the oxidation resistance of these materials. So it's a very challenging problem where you want these materials to be stable at very high temperatures. At the same time, you want to make them work for a long time. Otherwise, the mission will be a failure. And ceramics are always not so easy. And when you're looking at rocket programs, launch vehicle programs, it's an extremely expensive program, and any failure in the material, I think it's very disastrous. So therefore, one has to be very careful about that. We have done some preliminary experiments on making these coatings. You can see an uncoated steel substrate and uncoated alumina, and then we have coated it with polymer and converted into ceramic, and then we have tested it. I'll just show you a video. Maybe it will be nice to see the video and get an idea. Yeah, so this was basically to show you, I think this was basically to show you how we can make such coatings from precursor stage to making coatings on steel, metal substrates, and as well as ceramic substrates. So in order to make them, in order to be self-reliant and not to be dependent on any foreign companies, so we had to start our own company. We started a company called Saratatva Inotech Limited, so that we can be completely independent and make our own precursors. So we started this company very recently. In fact, it's just 6 months old, where one of my postdoctoral researchers who had a doctoral degree from Indian Space Research Organization, and his wife, who also had a doctorate degree from Indian Space Research Organization, we all came together, and Raghunath Sharma is a PhD student working with me, and we all joined together and started this company. And you will appreciate the fact that these materials, these are new materials, and we need to know the thermodynamic stability of these materials. And we wanted to have Professor Hari Kumar on board, because he is an expert in thermodynamic calculations. He uses calculation of phase diagram tool, CalFAD, and which helps us to establish phase stability of these materials, and therefore he was part of this company. And now we are the first company in India which can make such polymeric precursors which can be used to make ceramic materials for strategic applications. Now, of course, right now we are interested to cater these materials only to the Indian market, because at this point of time we do not know whether we will have permission to sell it outside this country. But at this moment, we are now catering it to the Indian market, particularly to the space and the defense industry. Just to give you again an idea, so these are how the precursors would look like. And if it's a non-oxide precursors, then we have to be very careful. They are oxygen sensitive. You have to make sure that they don't get contaminated with oxygen. And this is a small, piece of boron carbide materials that we have developed in the lab for armor applications. You know that steel armor is very heavy. It's not really the best thing to have steel armors. And the defense in particular, both the tanks, battle tanks, as well as human shields, armors, require very light and at the same time impact resistant materials. So boron carbide is an extremely a material which has been tested and proved to be good for such armor applications. So we have now started to make these boron carbide materials in the lab, and now we are in discussion with the Indian Army to transfer the technology to make such armors. So this is again to give you an idea of different kinds of precursors, polymeric precursors that we can produce in the lab. And many of these things are not commercially available in any part of the world. So that gives us a lot of advantage, because we can make these materials and whatever materials that we want to make, we are now completely independent. And that gives us a lot of advantage in not depending on anybody as far as material development is concerned. Simply because they're not commercially available, or they will be under embargo, and India cannot acquire them either from Japan or from Europe or from the United States. So this is what we are right now. And in recent times, we have also made our own small ceramic fiber spinning machine for short fibers. And now this is one of the first products that we have developed, and we have already started to sell it. And this works on centrifugal fiber spinning technique, and it challenges the electro spinning technique. I think many of you might have heard of electro spinning technique for making ceramic fibers. But the advantage of using centrifugal fiber spinning is it's extremely fast. You can make a lot of fibers. For example, the production rate is 1 gram per minute per nozzle, compared to electrospinning, which is 0.1 gram per hour. So this gives us a lot of advantage in industrialization of ceramic fiber technology. For example,
ceramic and
I just want to show you a video.
Ceramic and polymer fibers form the core of the key strategic applications in aerospace, defense, energy, electronics, filters, and textile sectors. The face mask, an essential accessory today, is made with polymer and ceramic nanofibers. Current manufacturing techniques are loaded with disadvantages such as limited material choices, unsafe operating conditions, and poor throughput. IIT Madras, an institute of eminence where innovation meets technology, has now incubated a first-of-its-kind ceramic materials-based startup, Cera Tattva Innotech Private Limited, originating from the Laboratory for High-Performance Ceramics in the Department of Metallurgical and Material Engineering. Cera Tattva brings into the market a centrifugal spinning unit, the first-generation ultra spinner with a TR level of 9 that wipes off all problems in the existing traditional fiber spinning technologies. Meet the ultra spinner, India's first commercially available centrifugal spinning unit. 1,000 times higher output than any other technology, user-friendly and high-voltage-free, safe operating conditions, integrated UV curing of fiber mats, clog-free operation, easily tailorable fiber diameter and morphology, producing both polymer and ceramic fiber mats in a matter of minutes. The Ultra Spinner also handles advanced functional ceramic oxide fibers and polymer-derived ceramics. The versatile and future-centric design enables extension to other materials too. The Ultra Spinner, the game changer from an IIT Madras research stable, is ready to disrupt the industry of polymer and ceramic fiber manufacturing. With its unique amalgamation of safety and high throughput, it is ideal to both industry and academia alike.
Yeah, so which means now we can actually make both polymer fibers, fiber mats, including ceramic oxide and non-oxide ceramic fiber mats, and we are now in both commercialized state. So we are already selling it within the country, making them. Now the biggest challenge is still to make long ceramic fiber filaments, which I initially talked about, like making very long silicon carbide filaments. That is still a big challenge. We are right now, we have developed a small prototype towards it, and hopefully, we succeed, because that's a very important thing for us to towards strategic self-reliance. So I think I'll stop here. If there are any questions, I would like to take these questions. I think I have just stopped 25 minutes. But if there are any questions, I would be very happy to take the questions.
If anyone has a question, please use the raise hand button.
I mean, I just wanted to say, I assume that a lot of guests here are metallurgists. It's not so easy to make this in metallurgy department because I'm a metallurgist, and it's not so easy because, as I said, this kind of work requires a lot of expertise in different fields and not so easy to get everybody in one single place. Um, on the one side, you have materials chemistry. On the other side, you require the knowledge in ceramic science. And when you're developing new materials, then you require knowledge in thermodynamics to understand what material is stable at what temperature. And then at the same time, you require engineering skills to translate what you do in the lab to technology. So it is really, really a big challenge to bring all kinds of people together. And it took me I joined IIT Madras 15 years back when I came back from Germany. So it took me nearly 15 years to come to the stage, even in India here. So it's a challenging job, but then that makes us really go forward with some motivation to do something very interesting. And particularly, the interest becomes more when it is not available to us. Let's say if a particular material is not given to India, so that means we are forced to make them inside in the country. So which is a good thing because when somebody doesn't give, that gives a lot of motivation for us to make it within the country. Yeah. I mean, if I don't know, it was too much of chemistry for you, but I tried to reduce as much chemistry-related slides as possible so that we keep it more technology-oriented. But if there are very generic questions also, I'll be very happy to answer.
Okay, thank you very much, Dr. Ravi, for this great session.
Muhammad, there is some question.
You can open your mic and ask him.
Already I have to answering.
Yeah, I see there are two questions, but please ask them. Yeah.
Is carbon fiber safe like battery to environment?
Can you repeat the question, please?
Is silicon fiber safe like battery to environment?
Sorry, I'm not understanding. Can you speak slowly?
Is silicon fiber safe like battery to environment?
I don't know if I got your question properly. Are you asking whether these questions can be used in different environments? I don't know, but what your question was, but these fibers are non-oxide fibers, so they have to be produced in inert environment. Otherwise, they get oxidized. So, for example, silicon carbide fiber has to be produced in a completely non-oxidative environment, completely inert environment. Because any incorporation of oxygen in silicon carbide will reduce the high temperature capability. I'm not sure whether I answered your question or whether I understood your question, but I've attempted. Yeah. Yes, please. The next one. You have any more questions?
If anyone has a question, please open your mic, and no one has a question. Thank you very much, Ravi, for this great session. Thank you very much. Yeah.
Yeah, thank you. Thank you very much for the invitation. It was great being with you. Thank you very much.